The 1994 Nobel Prize in Physics recognized Bertram, Neville Brockhouse, and Clifford Glenwood Shull for their pioneering work in developing neutron scattering techniques. This award acknowledged their independent yet complementary contributions to a field that has since become indispensable for probing the structure and dynamics of condensed matter. Brockhouse's development of neutron spectrometry allowed for the detailed study of atomic and molecular motions, while Shull's creation of neutron diffraction techniques revealed the arrangement of atoms within materials. Their innovations collectively provided unprecedented insights into the fundamental properties of matter at the atomic scale. Prior to Brockhouse and Shull's work, X-ray diffraction was the primary tool for determining crystal structures. Max von Laue, William Henry Bragg, and William Lawrence Bragg had established the foundations of X-ray crystallography in the early 20th century, demonstrating that X-rays could be diffracted by crystals, revealing the periodic arrangement of atoms. This technique proved invaluable for determining the structures of numerous materials, from simple salts to complex organic molecules such as DNA. However, X-rays interact primarily with the electron cloud surrounding an atom, making it difficult to accurately determine the positions of light atoms in the presence of heavier ones. Furthermore, X-rays are insensitive to isotopes and elements with similar atomic numbers. Finally, X-rays provide only information about the static structure, offering little insight into the dynamics of atomic motion. Neutrons, on the other hand, interact directly with the nuclei of atoms through the strong nuclear force. This interaction is independent of the atomic number, meaning that neutrons are equally sensitive to light and heavy atoms. Moreover, neutrons possess a magnetic moment, allowing them to probe magnetic structures and excitations. The wavelength of thermal neutrons, those in thermal equilibrium with their surroundings, is comparable to the interatomic spacing in solids, making them ideal for diffraction experiments. The energy of thermal neutrons is also comparable to the energies of atomic vibrations and other low-energy excitations in solids, enabling the study of dynamics through inelastic scattering. Clifford Shull's contribution centered on developing neutron diffraction as a powerful tool for determining crystal structures and magnetic ordering. In the mid-1940s, following his wartime work on radar at Bell Laboratories, Shull joined Ernest Warren at the Oak Ridge National Laboratory. Together, they embarked on a systematic investigation of neutron diffraction, building upon earlier, less precise experiments conducted by others. One of their key achievements was the development of high-flux neutron sources and sophisticated instrumentation for detecting and analyzing the scattered neutrons. Using the Oak Ridge graphite reactor, they demonstrated the power of neutron diffraction for precisely determining the positions of atoms in crystalline materials. A particularly significant application of Shull's neutron diffraction technique was the study of magnetic materials. Neutrons, possessing a magnetic moment, interact with the magnetic fields within a material, allowing for the determination of the magnetic structure, that is, the arrangement of atomic magnetic moments. Shull and his colleagues demonstrated that neutron diffraction could reveal the existence of antiferromagnetism. This is a state in which neighboring atomic magnetic moments align in opposite directions, resulting in a net zero magnetic moment for the material as a whole. Prior to Shull's work, the existence of antiferromagnetism had been theoretically predicted, but it had proven difficult to confirm experimentally. Neutron diffraction provided the definitive evidence for this novel magnetic order, opening up a new avenue of research in condensed matter physics. Shull's meticulous experiments established neutron diffraction as a quantitative and reliable technique. His work provided the foundation for countless subsequent studies of crystal structures, magnetic ordering, and other structural phenomena in a wide range of materials. The impact of his work is evident in the widespread use of neutron diffraction facilities around the world, where researchers continue to apply his techniques to investigate everything from superconductors to complex biological molecules. While Shull focused on the structural aspects of materials, Bertram Brockhouse pioneered the development of neutron spectrometry for studying atomic and molecular motions. Brockhouse, working at the Chalk River Nuclear Laboratories in Canada, recognized the potential of using inelastic neutron scattering to probe the dynamics of condensed matter. In inelastic scattering, neutrons exchange energy with a sample, either gaining or losing energy depending on whether they excite or de-excite a particular mode of motion. By measuring the energy and momentum of the scattered neutrons, one can determine the energy and momentum of the excitations in the material. Brockhouse invented the triple-axis spectrometer, an instrument that allows for precise control and measurement of the incident and scattered neutron energies and angles. The triple-axis spectrometer employs the successive crystal monocreators and analyzers to select and analyze the neutron beam, providing unprecedented resolution in both energy and momentum. Using this instrument, Brockhouse performed pioneering studies of phonons, the quantized vibrations of atoms in a crystal lattice. He demonstrated that the dispersion relation, the relationship between the energy and momentum of phonons, could be measured directly using inelastic neutron scattering. This provided invaluable information about the interatomic forces and the elastic properties of materials. Beyond phonons, Brockhouse also used neutron spectrometry to study other types of excitations in solids, including magnons, the quantized excitations of magnetic systems, and rotons, peculiar excitations observed in superfluid helium. His work revealed the microscopic details of these excitations and their role in determining the macroscopic properties of materials. The triple-axis spectrometer and its subsequent refinements became the workhorse of neutron spectroscopy, enabling researchers to study a wide array of dynamic phenomena in condensed matter systems. The impact of Brockhouse's work extends far beyond the specific materials he studied. His development of neutron spectrometry provided a general method for probing the dynamics of matter at the atomic scale. This technique has been applied to study everything from the vibrations of proteins to the diffusion of atoms in liquids. Neutron scattering continues as an indispensable tool for understanding the fundamental properties of materials and for developing new technologies. The convergence of Shull's neutron diffraction and Brockhouse's neutron spectrometry marked a pivotal moment in condensed matter physics. These complementary techniques offered a comprehensive view of materials, revealing both the static arrangement of atoms and their dynamic behavior. The ability to simultaneously probe structure and dynamics provided unprecedented insights into the fundamental properties of matter and paved the way for numerous advances in materials science, chemistry, and biology. Consider the study of high-temperature superconductors. These materials exhibit superconductivity at temperatures far higher than conventional superconductors, defying explanation by the existing Bardeen-Cooper-Schrieffer theory. Neutron scattering, employing both diffraction and spectrometry, has played a crucial role in understanding the complex interplay of structure, magnetism, and electronic properties that underlie high-temperature superconductivity. Neutron diffraction has revealed subtle structural distortions and magnetic ordering patterns in these materials, while neutron spectrometry has probed the vibrational modes and magnetic excitations that are thought to be essential for the pairing of electrons responsible for superconductivity. Another example is the study of polymers. Polymers are long-chain molecules that exhibit a wide range of properties depending on their structure and dynamics. Neutron scattering, utilizing both diffraction and spectrometry, has provided valuable insights into the conformation of polymer chains, their interactions with each other, and their dynamic behavior. Neutron diffraction can reveal the arrangement of polymer chains in amorphous and crystalline phases. Neutron spectrometry can probe the vibrational modes and the diffusion of polymer segments, providing information about the viscoelastic properties of these materials. The impact of neutron scattering extends beyond fundamental research. It has also found applications in a wide range of technological areas. For example, neutron radiography, a technique based on the attenuation of neutron beams by different materials, is used for non-destructive testing of aircraft components, bridges, and other structures. Neutron activation analysis, a technique based on the detection of gamma rays emitted by radioactive isotopes produced by neutron irradiation, is used for determining the elemental composition of materials. The development of neutron scattering techniques by Shull and Brockhouse was a triumph of experimental physics. Their ingenuity and dedication opened up a new window into the microscopic world, providing powerful tools for understanding the structure and dynamics of matter. Their work has had a profound and lasting impact on science and technology, shaping our understanding of the fundamental properties of materials and paving the way for countless innovations. The 1994 Nobel Prize in Physics served as a well-deserved recognition of their remarkable achievements.